record. Okay. So here is the problem. So we want to cover. So this is about covering a chessboard. No, I did not do BMath. I did from CMI. Yeah, I did get into BMath, but I didn't go for that. Yeah, that is in Bangalore. So I chose CMI. Yes. I don't know. I thought that there is more freedom at CMI, but I think the biggest reason would have been that I had some friends at CMI. Okay, some seniors whom I knew. So I was like, let's go there. Yeah, just that was the main thing I think. Because beforehand I did not know which one was better. Which one would be better. All right. So let's see. So we are trying to cover a chessboard. So uh, let's say that you have a 4x4. So maybe that is not. Oh yes, I shared the screen before. So let's take a 4x4 chessboard. This would also, it's supposed to be done by induction. Let's see. So let's say we have a 4x4 chessboard. Now, I select a cell at random, and let's say I remove it. Let's say I take this cell and I remove it. So maybe so this is no more present. Remove one cell, and now is it possible? So I will be giving a certain shape, and then you would have to see if it is possible to cover with that using copies of that shape. This is a standard induction question, which is slightly non-standard, but standard among the non-standard. Is it possible to cover the remaining? Checking it in the morning, it was working well. Is it possible to cover it using? So we would want to use this shape. Obviously, I mean, this shape means you can use this shape and rotations of it. Okay, so that is not a problem. And the other rotation, 2 more rotations that you would have. So see if this looks that can be done or not. So covering meaning that if you use this shape only, and obviously no overlaps, otherwise it's trivial. So maybe the better word is to tile, not cover. So let's say that I've removed the red one for a minute, and let's see if you can cover it in this case. Yeah, then we can. Yeah, but any one type. So do you think it can be covered, or So can you say, you can give me a covering that works? Mhm. Second one meaning you can say like the cell number sort of one. It's like a array, a matrix. One comma three, four, and two. This one. Okay. So you want to cover this with a L like this. Okay. Ah, this one then. Mhm. Uh-huh. Right. Maybe some other color. Mhm. Yeah, and then it is. Yeah, good. Nice. So it can be done. Okay. Nice. And then I think you can easily prove that for any cell removed, it can be done. Okay, so let's assume that. Okay. So here I will change this to any. So this much is fine. This is easy. This is just basic observation. Any one tile removed. Yeah. So gradually we'll just make the problem more interesting. Now I want to replace this 4 by 4. If I replace it 5 by 5, do you think this can be done? Again, one cell removed from a 5 by 5. Maybe we'll have to draw a different picture. This is not a part of the official question, but I'm just wondering if this can be done. The official question has a more specific generalization, which is proof by induction. We'll get there. Okay, why? Yeah, it seems like it is maybe not possible. Um, yeah, but I don't know. So, so can you say that for 6 by 6? I think this one is easier. Same question with 6 by 6. Right. Yes, certainly not possible, right? So that is the thing. So for 3n by 3n, it is not possible. But then for any other n, I mean, for any other n, this n square many tiles, right? This is always going to leave a remainder 1 when divided by 3. We have done that, and you can check that, right? It never leaves a remainder 2, a square number, right? When divided by 3. And so this is 1 modulo 3. And so that way there is no obstruction. Okay. Like for 7 by 7, 8 by 8, 10 by 10, 11 by 11. The number is always matching. Okay, 11 square minus 1 is divisible by 3, and 13 square minus 1 also divisible. But then is it possible or not? You have to think. So try this for homework. Okay. Maybe you can spend some time thinking about this. Whether for 5 by 5, maybe first 5 by 5 and 7 by 7. See if you can say something. Okay, I am not able to so far. So maybe I think later. So this is a good question to think. But then the official question is, which is much more standard and easy, is generalization in other direction where you generalize 2 by 2, 4 by 4. Now this is something that we have to do now. So, and let me not say possible, let me say it is possible, and then I just want you to prove that it is possible, because not everything can be done at once. It gets hard. So let me say that it is possible to prove that it's possible to tile. Think about this. 2 by 2, 4 by 4 we have done. Now you have to try to generalize. Just try this and just come. Yes. Okay. So any ideas how you can do it? So think inductively. Okay. So you have to assume for 2 to the, let's say 2 to the n times 2 to the n, and you have to try to prove the higher case. So maybe this is the first time that you'll be doing this kind of induction. So meanwhile, I'll just write a statement. So we cannot just give a direct one-step construction. We'll have to kind of use the construction for n equal to k. So now you have a 2 to the k plus 1 by 2 to the k plus 1 board. And maybe somewhere one cell is removed. I don't know. So the question thing really is now you have a 2 to the k plus 1 by 2 to the k plus 1 board. I mean, how are you going to reduce this problem to 2 to the k? Right, so that you can use that 2 to the k knowledge. Right? What's the most natural way to break it up into 2 to the k case, into the lower case? How do you break this into the lower? What's the natural construction? And you would see that the natural construction is, and I will not finish. Huh? Uh, yes, which one? So to remove what? Not 2, you mean 2 to the k? Yes, 2 power k times 2 power k. Yeah. Yeah, so either you remove, so basically it's 4 times, right? You agree that this is obviously 4 times. I mean, 4 times this is this. Right, in the morning, I checked something. I have to also use this in an interview, so I have to test a better word. Right? 4 times. So now, so the remove, like, then you have to remove many of them. If you want to remove, right? Let's see. So you think, try to use. So you don't have to removing it. Maybe that's one way, but necessarily you don't have to remove. You may you may reduce this to several 2 to the power k times 2 to the power k. Case. So what's the natural way to split this into kind of 4 parts, right? That way is one way to get to the k times 2 to the k blocks. Or Yes, I mean it's the most natural thing to just break it. Yes, just the most natural way, right? That is the thing one should think first. What's the most uh, you know regular way? Right? This is just the way you should break it up into equal number of blocks. Now this one, maybe this part can readily be tiled. Yeah, because this is a 2 to the k times 2 to the k block, and it has one tile removed. So it is our previous case. It has one tile removed is important. So that is done. That one is tiled. Okay. Now how do we tile the rest? The rest three. So maybe I can draw a better picture. Picture is not. Right? This part is done. This right corner, upper right corner. This part is done. It is 2 to the k size. How about these three? That's also an L. Yes, right? It just turns out. And these are also 2 to the k size. So yes, three of them. The numbers will match, but you have to find a tiling that actually works. And I'll just make this one. So extend this a little bit. So these are all 4 by 4. Uh, but one of them meaning like one of those three. But separately they cannot be tiled. Right. Yes. I mean I'm saying that for example, this one, it cannot be tiled by these shapes alone. And obviously right, the size even doesn't, yeah. And also what we have proved, as you know, is if you remove one from that, then you can tile that. If you remove one from each of them, then you can tile them. If you can remove one from this, one from this, then you can tile them by induction. So corner meaning this corner. Yeah, and then you are done. So in one, yeah, yes, that's right. In one shot, you have to remove. So it's just that I said it in a certain way, right? The last, yeah, but that's the thing. If you just follow the natural thing, okay, but obviously practice a lot. So this example is from this very obviously this is a standard example you will find in Arthur Angel also and so on. But this is the book from which you can try other problems. So I've told you about this book earlier. It's Mathematical Circle. So this has this induction chapter. It has a different flavor than some of the other books. So this chapter, and it's very instructive. Like it has a lot of word talking, and so it's very easy to read. And yeah, so oh yeah, it's not showing. Yeah, because that is because I was just yes, mathematical circles. So I'll just show it. Just, I mean, either way, you could just try from anywhere you get your hands on. But this is a very because it's very easy to read. They have a lot of words and details, and so and different examples are of a different nature than yeah. Okay. All right. So then let's back. This is one example I did. Okay. So let's see what we should do. The 5 by 5 case, it looks like it's not possible, right? 5 by, but that is something that I also think about. Okay, then let's try the next one. So the next is the screen share. Yes. Yeah. Next one is this. So again, this starts with a very easy thing. So you know that 3 divides this 1 1 1. Can you show that 9 divides this if there are 9 ones? So maybe you can say that, but let's just try. Let's just prove it from scratch. That's the. I mean, you can say that. That's correct, obviously. But mhm. No, it won't. It won't go to 9 powers. Will it go till 9 powers or 8 powers? There are 9 ones. Yeah, it goes till 8 powers, and this is a very this mistake we make very often in MCQs. I mean, I have made it many times. So yeah, okay. So this is what this number exactly is. So that is just from the definition of base expansion and so on, and the meaning of the number. 9 plus 9 plus 1. Okay. You mean you write each of the tens like that? Okay. Right. Ah. Mhm. Ah. Okay. Yeah. Okay. Okay. I understand. Right. Some. Right. And so then it will indeed work. Okay. So right. This is correct. No, no, this is fine. It's okay. We'll see. If you need induction, eventually you will need induction. So far, it's fine because just. Yeah. But when it comes to show for all numbers or show for some all numbers, if it's asked, then obviously you have to use induction. And if it's an arbitrary large number like 53 ones, and then it, then it's like if since that is true for all, then maybe induction is a better way to get to that. We'll see. So this is fine. Now we can try to just generalize this and see if what reasoning you can give. 27 ones. Right? So the exact same reasoning you gave earlier might not extend, right? So you have to adjust and see. Maybe the powers of 10 approach you can use. So you can be flexible. It's not that you have to use it. Huh? Right, right. Yeah, but why will that be divisible by 27? The rest will be 9 nines. That's the problem. Now we have What the previous one, the 9 one is the base case, it is split by 9. Uh, yeah, you can take, let's say both of them are true, we have already proved them. But how are you going to use that? The main thing is that how are you, like we did earlier, how do you break this problem if that's what you're going to do? Apply induction. How are you going to break this problem with the case of 9? That is the, then only you can use the base case or let's say the previous to build on. And then you can write the same thing for k plus 1. But basically, the point should be, the attempt should be to try to prove this divisibility by 27 using the previous two things. If you have to go by this inductive approach, then you should be able to do that here. So, like one way is maybe to write this as like 9 1, and then you can again use 9 1s times 10 to the, so it should be 10 to the what? 10 to the 9 or something? Yeah, yeah, certainly. Yeah. And you see like this. So this is what I'm just thinking is this one way to break the, to try to reduce this to previous cases. Several yeah, you understand. So, but will it be useful, that you have to see? But this is the way induction might, might work. It has to work. Maybe 18. Yeah. Just find the tiling question. This question. Find some coloring, some way to color it, create a contradiction. And then, uh, n should be divisible by 3. What is the n? No, so here so far there is no n, right? It is just, see if you can see that. Here, don't think about the n, maybe just see if you can conclude that this quantity is divisible by 27 from the divisibility by 9. So you know that this is divisible by 9, this is divisible by 9, and this is divisible by 9, right? Can you use that? That is the question. So, I mean, the natural thing again here to do, I mean, you can see that each of them is divisible by 9, right? Each of those three commands. So to use that, I would pull it out, right? You take that out and now see if you can get something. It is it? So why is it? So why is it? And that's what we should do. So, but so that we get the extra 3 that we need. Line. So what? But why is it divisible by 3? Why is this quantity divisible by 3? Mm-hmm. 8, 9. Oh, okay, okay. By that reasoning you gave. Okay, nice, nice. And so then, I mean, then I suppose then you also understand how you can now generalize, right? Like k, if there are k ones, then it will be divisible by 9 to the just in this because you understand how you are building it, right? I mean, there are induction is what I mean. It's like it's sort of you're using this recurrence idea to build to the next one, right? Right. Sometimes induction is used to prove some obvious things also, just to make things rigorous. But here the inductive idea is being used, right, to build on to the next. So this is a so that's the first question was also like that. This is also good, and now you can. And then you can also try this question. Now, this I don't know if it can be done by induction, but I hope this is true. If let's say if uh, if and you can try this. If the sum of digits of of n is divisible by 3 to the k, then n is divisible. So this is like a generalization, right? Our number was a very special number. Some of the digits was equal to 3 to the k. But now any general number, some of the digits is equal, or let's you can try for equal also, or in general divisible by 3 to the k. Uh, then n is divisible by this divisibility test. This is more like a number theory question. Okay. You can try to see how to do this for homework. No, so it is similar. It is similar. So basically, what I would have just done in this situation from here is maybe I mean this is obviously so this is divisible by 3 is more obvious by one way to say it is that this is 10 is 1 modulo 3, right? And so 10 to the 8, 18 is living remainder 1, and this is also living remainder 1, and this is so it is divisible by that part. For that part, I might have done this. Okay. But it's the same thing. Yeah, what you have said. Yeah. Yeah, and yes, and that's all you will get. You will not get that is divisible by 9. You will not get that, right? In this, yeah, because there will be only 3 ones. All right. So that's fine in that question. So then these are the 2 different type of questions we did. Let's see. Let's do. So first, let me define what is a convex. Convex n-gon. So n-gon, just n vertices and n sides. What is the? So do you know what we would call convex n-gon? No? All right. So convex simply means that every interior angle, each of these angles, right? Just naturally, it's just less than 180 degrees. Okay. So convex means that each interior angle. I mean, there is a better reason why this is called convex, but uh, less than 1. So you see the second picture I've drawn, it is not convex because this interior angle that we are looking at. This is still not a very perfect definition, but this is enough for our purpose. Now, can you say what will be the sum of these angles? 1, 2, 3, 4, 5. Is it anything that you can say for the sum of these angles? Right? Uh-huh. No. The interior angles, right? So what should they add up? So if there are, let's say, if there are 6 sides as there are in this picture, right? I mean, it's like in a triangle, they add up to 180. Yeah, you can try proving that. It's a good small little exercise to prove why it adds. But this is a fact that we know that adds up to 180. In a quadrilateral, we know that it adds up to 360, right? So just from that reasoning, in a 6-sided, what should it add up? That is to begin with. Right. So how many triangles are you going to get? That's a precise number. So can you say how many? So how many triangles will you get? So that number is pretty precise. It cannot be changed. So it's just 4 triangles. It's n minus 2. That's a formula which you, yeah, at some point we all have done. But yeah, forget this. And so it's 4, right? 4 into 1. This is okay. Simple. Now, my question is, at most, how many of these can be used? At most, how many of these angles can be acute? So why I'm asking this question is, it seems like not all of them can be acute, right? Like you can just ask that question for a quadrilateral first, right? In a quadrilateral, how many acute angles can you draw? 2, 3, 4. Is it possible that 4 of them are not, all of them are acute, all angles? That is certainly not possible, right? You just cannot draw a triangle, a quadrilateral. You can draw a square, acute to, let's say, less than 90, I mean, acute, but less than. You can draw like 4, right? These are 90, but you cannot make all 4 less than 90, right? Like, so you can make at most 2. In a quadrilateral, it is at most. In a hexagon, as we have drawn, any arbitrary hexagon, how many acute angles can you possibly draw? Means at max. Yeah. No, opposite I don't have to add up to 180, but still it is not. So that happens in a cyclic quadrilateral, right? And so obviously in general, the opposite sides don't have to add up to 1. It is both less than. Yeah. But then it is at most, it should be at most 2. So what happens if 3 of them are less than are acute? Is it? I mean, it just looks impossible, right? Yeah. How do you prove that 3 of them cannot be acute? Uh, hmm. So I mean, certainly all 4 cannot be acute. Otherwise, it won't add up to 360. But yeah, this is the question. So I don't know. So a quadrilateral. three acute angles. Just 1 minute. I don't know. So I'm just thinking. This looks wrong. So there is more to the geometry. Yes. 360. No, exterior angles add up to 360 because you're going in a circle. Um, yeah, and not more than that. So if you have angles, and so if this is more than 90, and this is also more than 90, and this is also more than 90. But it doesn't create a problem, right? It is just more than 180. Sorry, more than 270. Which is not a problem. But somehow we are missing something. No, it's not some parallelogram. Yeah, that way we certainly this should be an easy fact. Somehow, or I think it is just possible, right? Yeah, I think it might just be possible. Is it? So yeah, but you couldn't draw, right? And why is it not possible? So if I take this image and then that, maybe that. Yeah, but that's not part of. So I'm thinking that if we have a maybe that way we can arrive at the contradiction that is not possible. So imagine you have one ray like this, which is one ray is acute, okay? And then you have another acute ray, okay? And let's say just this here. Now, if we try to place this acute ray here and place it there, let's say place it like this, not to make it parallel or anything, just to place So obviously, the angle, this angle and this angle are both less than 90. But then, if I just rotate this thing, just rotate this a little bit, and then I am decreasing this angle also. So then, why is it that I cannot make that less than 90? Right, you see. So if I, the limit will be when this is 90. And this is less than, and because these two angles don't change, right, when I rotate this one. So then why can't I make it less than less? Why can't I make this less than 90? I can, right? Yeah, like certainly. I think is there any problem if I make it less than 90? I have this 90 degrees. Oh, there does seem to be some problem. I have this 90 degrees. I bring this here and I make this. If I shift it and I make this 90, and then I yeah, I mean I don't know, it seems possible. Maybe we can look at it another view from a different way. So if I make mm, I'm just thinking, see, like if we make like this, right? This is fine. Now this is less than 90 and this is also less than 90. I mean, this is a triangle. No, so what I'm trying to say is that now if I just change this angle slightly so that it becomes like this, little bit, it will still remain acute. Um, but yeah, but then this angle has increased. Right. I mean, change it, and if I, or maybe I can say that, that's right. Uh, no, so if I shift this like this here, this angle will remain as it is, but um, then this angle is okay, and this angle is okay. Okay, this is x. I'm just trying. I mean, I just trying to get a contradiction. This is x, and this is x. Um, in then this. Let's change picture. No, that is certainly not x. Right. Uh, Yeah. No, so this angle is different. So if you can show that this angle now becomes, no, but it does not, right? Yeah, it doesn't become more than, yeah, so it's possible, right? Because this total angle that you get is less than 90. That is clear because it's part of a part of a right triangle, right? This is less than 90. And then similarly, this angle is also less than 90. And this angle is, well, I mean, it is 90, but you can just ever so slightly change it and it will not really, yeah, it will not make this obtuse. It will not make it obtuse, right? And then you do get a picture in which you have three, right? Yeah, I think that is, I don't know, is it not correct? Because then it seems, because see, I can just change this a little bit, right? And that's it, right? I mean, this angle is less than 90, this angle is less than 90, this angle is also less than. Huh. Yeah. Which angle? So this angle, yeah, but it doesn't become obtuse. That is that, yeah, that is okay, right? It doesn't become obtuse. I mean, because it is far from becoming obtuse. This angle is, let's say, 45, and yeah, that is all because it has to make up this much to become, or at least this much before becoming obtuse, because it is that much less than 90 and so on. Yeah, but I think it's very strange. Well, anyways, we will try this next time. Yeah, the question was to show that, oh, yes, yeah, it is indeed possible. Yeah. So you see, we had this initial intuition that it is not possible, but that's wrong. And I think that's why we spent so much time in trying to prove that it is not possible. But anyways, we learned that it is possible. Yeah. What we want to, maybe what first thing you should try to do is to show that you cannot have more than three acute angles in any n-gon. That's the first thing we should try. Okay. In any n-gon, you cannot have, we have shown three, right? So that's what the question is harder than that, but first try to show that in any acute n-gon, you cannot have more than three acute angles. I think that is correct. And then the actual question is, which is just there in the book, is that there is always an n-gon for any n for which there is exactly three acute angles. Like the one we are trying to make now. Okay, I didn't read the question before, otherwise I would have known. It's good that I did not know. Yeah. So these are the things to try to prove. Yeah, and maybe you can read the solution also if need, see the hints. Read one line and then try if you get. Yeah, and then maybe next day you can explain it to me. Okay, that will be good, and so we can move faster into. I think it should be anyway. So yeah, these are the things. I will take a class tomorrow also. Yes, yes, mathematical circle. So you see, these questions are a little different type, right? You can understand already. Yeah, like different from the typical